and welcome to our very last What Physicists Do of the semester. So today I'm very excited to introduce my good friend Bolton Smith, who comes to us from Viavi Solutions in Santa Rosa. So he's a local. So V and I first met at San Francisco State, actually, where we worked in a research group together. That was back when I did quantum optics research. So there, at the time, at San Francisco State, V was working on his master's in physics. Before that, he had gotten his BA at Pepperdine, BA in physics. BS in physics. Oh, excuse me. He got his BS in physics from Pepperdine. So with that, he's here to tell you a little bit about his work at Viavi. So.
Hi guys, thank you Alex for the intro. I really appreciate you guys inviting me to speak here. Today I'm going to talk about the group that I work in Viavi Solutions, which is the Sensors and Spectroscopy group. The talk will go over a few things. I'll give a little bit on my background.
Can I ask, we don't amplify the voice in here, and so we're instructors all the time, so we're used to using,
Gotcha.
You mind using a professorial voice for the back of the room?
All right, I'll do my best. Everybody hear me all right back there? All right. I'll go through a little bit of my background, cover some of what Viavi Solutions does that I'm not really a part of, but then I'll focus more on the product that I work on, which is the Michener spectrometer, and kind of go through a little bit of the science that goes into this, including briefly touching on spectroscopy, thin film optical coatings, spectral data analysis. And then I'll go over some of the newer technology we're working on, which is the HFA, or a hyperspectral filter array. And then lastly, I'll just kind of go over my specific roles and responsibilities with that. So my background information, Alex did a good introduction, but I usually go by V. I've been called V by my family, friends, professors, coworkers, so feel free. I did my bachelor's in physics at Pepperdine with a math minor, and then moved up to a less conservative school that has a pub on campus at San Francisco State. I went there from 2010 to 2014. And I got hired before I actually finished, so I didn't technically get my master's until this spring, when I finally kind of rounded up my advisors and got them all on a good day to do my defense, and finally accomplished that. Actually, the position I got was through my advisor. One of her former students worked at what was JDS Uniphase, and he gave her the heads up that there was a job opening. So she referred me. I got to go through and do an interview, get my resume up to date. Didn't actually think I'd get the job, but they gave me an offer, so I went ahead and took it. Going back and finishing was very difficult. So I'll just talk about my company, Viavi Solutions. This slide is a little outdated because since then things have been updated, but we have about 3,500 employees. I think now 61 global offices. I'm pretty sure we've passed $1 billion in annual revenue, and we're definitely past 2,000 in patents. But Viavi Solutions is, it's been around for now 71 or 72 years, and it's split up into two different segments. One is the NSC Network and Service Enablement, and they do a lot of network testing and measurements. I'm not involved in that at all, so I don't know much about what they do. They're based down in South Bay. And then here up in Santa Rosa is the OSP, Optical Security and Performance Products. And that's the group I'm in, and I'm in a subgroup of the Spectral Sensing group. But I was going to go over a little bit of what the Optical Security and Performance group does. The main thing is Viavi Solutions specializes in optical coatings. We do anti-reflection coatings. If you want something that doesn't have any glare, we usually do more of the higher end, more expensive things. We do bandpass filters to only select certain wavelengths. Linear variable filters, which I'll talk more about, but they transmit different wavelengths across the filter. Large scale optics, like this telescope here, a couple other things. Low angle shift, so if you shine light through a filter at angle of incidence of 0, then you're going to get a different transmission profile than if you change that angle of incidence. So we do a lot of low angle shifts so that transmission profile doesn't change that much. We pretty much specialize anywhere from visible to the long wave infrared. And there's also polarization control. So a couple of the applications for this is 3D sensing. So we do the filters and diffusers for a lot of 3D sensing applications. It started off in the Xbox Kinect. If you don't know what that was just a video game where it could sense basically movement of your body parts, and you could go like this, have you kick a soccer ball into a goal, or you could select things with your hands. But since then, things have improved. We've gone into topology measurements, LiDAR systems, and last year we actually acquired a company, RPC Photonics, which does specialized diffusers. And so the way that this 3D sensing works is you have a light source that shines basically some kind of pattern, and then you have a filter to only look at the light that's creating that pattern, and you have it come back to a sensor. You could reshape that pattern to figure out the distance away from things. LiDAR is similar. You shine out a light, you have a very fast sensor that could detect how far that light has traveled before it reflected and came back.
So is it basically radar with light? Is that what LiDAR is? Like light?
Let's see, LiDAR, that was...
Or is it an acronym? It just sounds like radar plus the word light.
Yeah. No, it's an acronym. I
Light,
forget.
distance, and ranging.
Light distance, okay, there it is, yeah. Another cool thing that my company does is specialized pigments. On all the currencies, like if you have a $100 bill and you go like this, and you can see that part of the bill changes colors as you look at it at a different angle. We actually do the pigments for that for over 100 different nations around the world. So if you see, the Australian money with the little hummingbird that changes colors, those are Viavi pigments. And there's also, used for more consumer things like cars. This was the structured blue, which got a lot of hype from Lexus. It's kind of cool because the pigments in here, none of the materials contain blue. It's just all the way that the light interacts with these pigments that reflects blue, or that could change color as you look at a different angle. So those are all cool, but I don't work on any of those really. What I work on is the Michener spectrometer. So it comes in a couple of different forms. We have the wired forms. There's the Michener 1700 ES. Its counterpart is the Michener On-Site or On-Site W. That's what I brought here. Then there's also Michener PAT, which is a process analytical technology. And it's basically meant to be on more of a process monitoring type of line. So we have a wired one and then also a wireless one. The top one communicates via Bluetooth, this one communicates via Wi-Fi. And I'm going to focus most of the talk on this Michener because there's a lot of science and engineering that go into this product. So I kind of just listed the bulk of it here. The main application is spectroscopy. It's a spectrometer, so I'll go a little bit into that. We have the special sauce is actually a thin film optical coating that's in it. A lot of optical design. There's some sensor technology, electronics. You could run the electronics with software, mechanical design, and machine learning and chemometrics to analyze the spectral data. So I figured I'd start off with what is spectroscopy. I'm sure many of you have a good idea of it, but in case you don't know or need a touch-up on it, from Lexio Dictionary, which is the first definition you find on Google, The branch of science, or spectroscopy, is the branch of science concerned with the investigation and measurement of spectra produced when matter interacts with or emits electromagnetic radiation. So I figured a good way to demonstrate what spectroscopy is to actually do a little Michener demo. So I have here the Michener on-site W. So let me just log in here. I gotta change this. Hopefully this all works. Okay, cool, awesome. Okay, so I also have here a bunch of different unknown white powders. Well, we know what they are because I've labeled them, but to the human eye, they're very hard to distinguish because they're all just the same color to us, right? So the first thing I do is it tells me I need to go on the reference and calibrate it. And so now I could go into one of these random samples. If I scan it, it'll tell me that the sample that it just scanned, it thinks is lactose. And I could pull it up, and those in the front row could verify it's lactose. Yeah, so you can see, right? Yeah. And so this is basically the... So here's like a spectrum of it. This is actually a process spectrum, but I'll go over that. If I do another one, for instance, here. So ibuprofen. Yeah, it is.
So these are all ground up different white powders, and the reference is something where you're teaching it how it, how things respond to light, so that you can compare it to how these other things are responding.
Right, exactly. So this reference scan, this is the raw counts. Basically there's a number of pixels here that each have a corresponding response and counts. This is a 16-bit detector, so it could go up to 65,535 counts. The reference that I used here is basically a flat response across the entire wavelength range. So when I scan this, I know what a flat line looks like. And then when I scan these that have some curvature, I could take out the actual reflectance spectrum based on what a flat spectrum looks like. I also do the same thing with the dark scan because you want to subtract any dark fixed pattern variation or things like that. But yeah, so that's the spectrometer. You can see the spectra. It basically uses these spectra to determine what that sample is. Will I need to unplug it on it if I switch back, you think?
No, probably not. Hopefully not. Good question.
Fast. All right, sweet.
Nice.
Okay, so now the question is, how does all of this work? Well, there is molecular vibrations, which is ways that molecules can absorb energy. And this just shows, a 3-atom molecule, shows all the different ways that it could store its energy. And if you use, if you use the simple harmonic or anharmonic oscillator approximation of what a molecule looks like, Schrodinger's equation will result in discrete energy states like we see here. And every discrete energy state corresponds to the energy of a type of photon or a type of light wave, right? Because here's our spectrum. You can see as your wavelength increases, your energy decreases, right? So what this tells us is there's different lights that this atom or this molecule can absorb. Now, of course, this is a very oversimplified model. This just looks at one particular molecule. It neglects if it's in a crystalline structure, more complex molecules, or different temperatures, etc. So the end result is a more complex energy band. But what happens is if you shine light on a material, some of that light will be reflected, some will be absorbed, some will get transmitted, not shown here, some will get scattered. But the amount of light that gets absorbed, if you shine broadband light on a material, for instance, this is aspirin. Aspirin's gonna absorb some of this light based on the energy that the molecule can store. So you could see somewhere here around maybe 1120 or so. It's a big absorption peak. So the way the Michener detects this is it does shine light on a material. I don't know if you saw the light come on, but it shines light on a material and it measures the reflected light off of that material. And you can actually go from reflection to absorption just using this simple equation. It's not a linear transformation, it's based on a log scale. It's kind of like the optical density if you've seen that. Yes?
So the light that it's shining is white light then, right? So it's shining across
Yeah, so
the full
we
spectrum?
use like a tungsten type light. So it's a broadband light that you can see some visible. A lot of the spectrum that's emitted is in the NIR region. Now going back to these discrete bands, there's a couple of definitions. We have the fundamental or the combination band, and that's just from the lowest energy state up to the very next one. That certain energy level is called fundamental or combination. The next one in the red goes to the second energy state, and that's the first overtone. Then you have second overtone and third overtone similarly. And what this looks like to us, or what this means, is we look at this wavelength range and we have a bunch of different types of common materials or common molecules that make up materials. You can see the top row is just water. The Michener region is right here between 900 and 1700 nanometers. So we mostly are looking at the second overtone region. A lot of times your first overtone or the combination band gives a lot more rich spectra, but it's also comes with a lot of complications also. And I thought this was kind of cool, just the evolution of spectrometers throughout the decades. So in the 70s, spectrometers were these ginormous things that are mounted against this wall. Later it evolved to this huge, basically the size of a giant desk. Then we kind of got down to printer size, got down to this, looks like a framing nailer or something. And now we're down to this little golf ball size. The kind of funny thing is now we're going back up in size a little bit, right? Because now from the golf ball, now we added a handle, we added a couple probes, and made it a little bulky to go onto different types of hardware. So these process units are actually meant to be basically fastened into certain types of process equipment. For instance, this one could go on a tumble blender in pharmaceutical plants. So as they mix their medication, you could lock this in and have it monitoring in real time, you know, if there's the right concentration of different materials, if there's any contaminants, and you could also even measure when the mixture is thoroughly blended. You know, this on-site W is designed to go out into the field, so it has to be ruggedized. We've sent it through waterproof testing, dustproof testing, different military grade shock and vibration and temperature testing. So yeah, what makes the Michener work is actually the optical coating that's in it. So I'm going to talk briefly, touch on a little bit of some thin film analysis here. So this soap bubble is a very common way of explaining what a thin film is, because the soap bubble itself is a thin film. You have air, a very thin layer of soap, and then air on the inside. So you have an interference pattern that results in basically a variety of reflected colors. So based on Maxwell's equations, you could calculate from an electromagnetic wave going from one type of material with one refractive index to another, you could calculate the reflection and transmission amplitudes. You could also calculate, I didn't put here, but you could also calculate the phase upon reflection of that light. But what gets tricky is once you add another layer there, right? Because now you have this first light that gets reflected, the transmitted light now hits another reflection, and that reflects. Now you have some that are transmitted here, some that are reflected, and it just gets really messy, right? Well, you could actually, using the principle of superposition, which is basically saying you consider all the waves in this location, you could determine reflection and transmission amplitude coefficients based on that. And actually what it comes out to be is it's basically a lot of linear algebra, right? You could say that this is one array. Every time you hit a layer, it's a matrix transformation. And once you get to the end, you could relate that first array to the last one. And actually, going further, if you have multiple layers, those could all be combined to be one identity matrix, or not identity matrix, but one equivalent matrix of multiple layers, but the effect of just one layer. So with these thin film coatings, what's really important is the thickness of this layer. For this example, I just chose an incident medium of air, which has a refractive index of 1, and then some substrate of glass, index refraction of 1.52, and then some thin layer with an index refraction of 1.38. So our phase thickness, basically saying if you have your light wave going through, the thickness depends on your wavelength, the physical thickness of your layer, and the index of refraction of that layer, which actually is also dependent on wavelength. But as you change that, you can see what your reflection looks like, right? So if that in one layer is exactly a quarter wave thick, then you could actually reduce your reflection down to about 1.25%, right? If that layer wasn't there, you'd be hitting about 4.25% reflection. But by adding that layer, you change that amount that's reflected, and therefore you change the amount that's transmitted. The main takeaway I want to get here is that layer thickness is really important to determine your wavelength that's transmitted. And the reason why I want to emphasize that is because with the Michener, we use a linear variable filter. And this linear variable filter is basically a filter whose thickness changes linearly, right? So you have a variable thickness that varies linearly with this filter. Well, if you put that directly on top of a pixel array, now every pixel under that detector, or under that filter, is going to see a different wavelength. Okay, so that's basically how the Michener operates and how we could determine a spectra using this Michener. So we shine light, we have some specialized optics to control the light to make it go through the filter properly, and then from there we could rearrange the pixels and basically perform wavelength calibrations to know which pixel corresponds to which wavelength. So the next topic is spectral data analysis, and this is important because now we've figured out how to collect spectra. What do we do with it, right? If I could scan this new material and I get this funky curve, how do we know what that material means? I mean, we could look up a bunch of different spectra and see, oh, I guess that one looks kind of like this other spectrum, but how do we actually do that mathematically to say how close is this spectrum to another one? Or how do we automate that decision? That's when we get into some pretty cool things. So there's chemometrics and machine learning, and a lot of this goes into this spectral analysis. So chemometrics is the use of mathematical and statistical methods to improve the understanding of chemical information and to correlate quality parameters or physical properties to analytical instrument data. And machine learning is a method of data analysis that automates analytical model building. It's a branch of artificial intelligence based on the idea that Systems can learn from data, identify patterns, and make decisions with minimal human intervention. So basically what we do is we use machine learning to build models for chemometric purposes, right? So we use machine learning techniques to build models, and those models could give us information on our chemical makeup, right? So I'm going to go over a little bit of one of these, which is principal component analysis. Sorry, one more definition for you guys. PCA is a statistical procedure that uses an orthogonal transformation to convert a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables called principal components. So a very simple case of this is just the axis rotation, right? If I have this set of data with given x and y values, well, you see that that's pretty correlated, right? As x increases, y increases. But if we rotate our axes, now all of a sudden, if we look at it with these dotted line axes, now we can see that they're no longer correlated. We capture most of the variance in our x. The y, the y initially went from about -30 to 30. Now it's only plus or minus 2, because all the variance was captured, most of the variance at least was captured in this new x-axis. So I'm going to go through a little bit more of this with our spectral data, but before I do, I just wanted to point out that there's different ways to look at spectral data, right? If we have 3 different types of samples, we could look at the wavelengths, and this is how we usually observe spectra. We could say, okay, wavelength 1, wavelength 2, and wavelength 3, but we could also turn those into independent variables and plot them together, right, where each wavelength now is an axis. And now instead of having these lines as graphs, we actually get certain points in this 3-dimensional space because there's 3 wavelengths. Right, so you could see that, for instance, the green, it's 1, 1, 2. So from here you go 1, 1, and go up 2. And that's just basically pretty straightforward. But what happens now when you have 125 wavelengths? Right, now this is all of the spectra from all of these white powders that we were looking at. How do we deal with this? Well, the first thing that's usually done that I haven't talked about is you process your spectra. In this case, I used just a simple first derivative. I used a smoothing algorithm, and I used a procedure called standard normal variate. A lot of this is to just remove a lot of sampling issues, but it's really just to get the raw shape of your spectrum without certain things. For instance, if I scan too close or too far, that might give your spectra a baseline. Well, you do first derivative, it takes that baseline right out, right? Because that's just a constant DC offset. The next step is we could actually perform principal component analysis, and now we could use only the first 2 principal components of that, which capture most of the variation across all that spectra. So in this case, the principal components, what it does is it performs a linear combination of all 125 wavelengths and creates a new axis with that. Then finds another orthogonal axis and does that basically 125 times. Each new axis captures most of the variance of the spectra. So the first axis would capture most of the variance, and the second axis would capture the rest of that variance, basically. Usually within the first three PC components, you're down to 99% of the variance captured. So that's just a very brief intro. A lot of the different machine learning techniques and algorithms are based on that principal component space, or at least some form of that, where you're doing a linear combination of different wavelengths in order to basically project your spectra as data points on a new set of axes. So there's different types. There's classification and there's regression. So classification, in this case, this is called support vector machine, but classification just determines, if I get a new data point, what material is that, right? So is this salt or sugar? Regression, that'll tell you concentration, what concentration of this material is in your sample. So is this, you could scan something and it'll say 30% sugar, 70% salt. Right, so you could have both discrete and continuous results here. In this case, support vector machine draws a boundary line based on the edge data points that are closest to it. So you always build a model by training your instrument beforehand with known data so it knows what to look for in new data. Okay, and then usually one of the main plots we look at with regression models is your reference value versus predicted. So this could be, for instance, your Brix value, or your sugar value in apple juice, for instance. You train with a bunch of different apple juices and you scan it to see how close you are on this line. So your actual value versus what your instrument predicts. So that's a good amount on Michener. One of the other things that we're doing is the hyperspectral filter array, or HFA. And this is relatively new technology. So these are some cool images of it. It's a really small array. It's a monolithic filter that's consisted of discrete channels, right? So each one of these channels transmits a different wavelength, all right? But it's all on the same filter. This is a cool microscopic view of one of these, or of a wafer consisting of these filters. So I could talk briefly about how these are fabricated. Well, we start off with a substrate. So if you put on photoresist, so let's say this top part here, you put on some photoresist and you could zap some off, which is the second layer here. Then when you put on when you deposit your coating, some of the coating goes directly on the substrate, some goes on the photoresist. Then you wash off that photoresist with some chemicals, and you're left with a pattern of the coating you want directly on your substrate. Well, with this product, with this filter, what we do is we deposit our first mirror on the substrate, and then we do different spacer levels. So you can see the first spacer, everything gets that first spacer level, and that sets our smallest wavelength. You cover half of it, put down your spacer 2, then you cover the two quarters, this quarter and that quarter, and you put on your spacer 3, and you're left with this step function that has different thicknesses and therefore transmits different wavelengths. So this is kind of the end result, is when you're shining broadband light on, only the wavelength corresponding to the transmission profile of that thickness gets transmitted. And this is actual data from our near-infrared filter array. I do have a little demo here that I could do. Let me make sure I get everything set up correctly before. It's not too much, but it's kind of cool. Just bear with me 1 second. Okay, so this is going in real time. All I have is a multicolored LED in here, or it's basically multiple LEDs. And what it does is it's recording the spectrum of the LED. And you can see when there's, for instance, cyan, it's going to be blue and green. When it's white, you see kind of a broad spectrum. So this is our color, our visible hyperspectral filter array. In red, you get that sharp red peak. And I did bring, this is the actual sensor it's on. It's a very tiny piece of equipment. The entire board and everything is also very small. So this is the entire thing here. So it has the driver, the LED, the sensor, filter, and it's meant to be extremely compact.
So why are there like different squares like on the sensor map?
So this is actually how the filter looks. If you remember on the slides, I showed how there's one filter with a bunch of channels in it. Each of those channels correspond to a different wavelength. So now you can see when these basically, actually you could even see on here, this says like 497, 475. So these are just showing which wavelengths are being illuminated in the 2D image. This is showing it reconstructed as spectra.
So are the colors on the sensor map, are they telling us like how much of that one is blue corresponding to like?
Yeah, so the one that's really red is going to be the highest peak here.
Okay, so red is like it's sensing a ton of light for that wavelength.
Yeah, exactly. Yeah, so that's that demo. It's a pretty cool, pretty neat product. I only have one more thing to go through basically, and that's just kind of my roles and responsibilities for these products. So I work on both the Michener and the hyperspectral filter array. With Microcar, I do a lot of the calibrations, whether it's wavelength or temperature or photometric. I do a lot of performance testing. So we, as I mentioned before, we sell into the pharmaceutical industry, and they have very high standards, as you could imagine, in terms of performance. So, trying to keep up to date with their requirements and making sure we meet those specs. I do some data analysis. A lot of it is troubleshooting. If a customer has an issue, they send over their data. I could look at the data and try to figure out what's going on. I do qualification, so I was down dunking this thing in water, sending it in the dust chamber, doing all kind of qualification testing. I manage the production software, so if we ever need to implement some new process or something new to characterize, I'm the one to put that in the software. I also make little software tools, application studies, and some optical designs. For instance, if we need to measure a specific type of sample, like a liquid sample, we would have some designs that would accommodate that kind of measurement. On the other hand, I'm juggling two projects, and the other one I'm also doing calibrations with wavelength. As you could imagine, putting that grid of filters onto a sensor, you have to figure out which groups of pixels correspond to which wavelengths. So I do a lot of that kind of calibration, performance testing, data analysis. This isn't the only sensor we use. We have other sensors we could test with our filters, so I do a lot of the evaluation there. Some test software and optical designs there. But yeah, that's what I do, and that's our company.
All right, so
Oh, yes, questions.
I wonder if you could talk more about getting that job, like what you were doing for your master's degree and how you kind of got paired up with this company.
Okay, yeah, sure. So, what's kind of funny, I was in the optics lab. I did nothing like the stuff I do now. But just having the optics background, I think, is really what got my foot in the door. But really, my advisor, her former student was working in the same department. He was actually my coworker for a while, but he's the one who reached out to her. At the time, I was still working on my thesis, and so what I did for my research was more nonlinear optics. So shooting a laser through some material, seeing how that light interacts and how it comes out on the other side. But I think having that background really helped. Another thing that actually I think helped is going in not expecting at all to get an offer, and so the pressure was off. In fact, I was like, I don't know I would want a job right now because I haven't finished school. I didn't want to have to deal with going back to school after getting the job. But yeah, the actual process of getting the job, so there was 2 phone interviews and then basically an 8-hour interview on site. They did ask a couple quiz questions, so be prepared.
Physics quiz questions?
Yeah, some of them not as complicated as you might think. Like some are kind of arbitrary. Oh, if there's a waterfall, which water is going to be hot or cold, the top or the bottom? And you have to explain your reasoning for it. So that was one of the fun ones. If you're in a boat and you have a lead box and you throw it off, how much is your boat going to rise, type of thing, you know. So so classic physics questions. But yeah, I don't know if there is that cover.
Yeah.
Yeah.
Do you see maybe a police officer using the micro NIR to deduce whether a white powder is cocaine or something?
Actually, yeah, that's a very feasible
I was thinking
application, I
that or
think.
like anthrax, right?
Yeah.
Oh, you're right.
Yeah.
No, seriously, if you find some random white powder in a box or something, yeah, you should probably test that. Yeah.
So I'm curious, what mode do you work in? Do you work mainly by yourself for a long period of time, or do you work in teams? And if teams, how large?
So our whole group is only maybe 7 people. It's a very small group for the Michener and the HFA, which is kind of cool in a way because we get to do a lot of different things. I feel very fortunate to be able to work with this because I get to touch on, like I mentioned, a bunch of different topics and engineering. But I'd say most of the time we're working alone, especially when it comes to like software data analysis. You do most of the work alone, and then you might present results with your teammates and get feedback and brainstorm things, but then you go back off on your own. There are some times where we do have to collaborate, especially when it comes to making kind of tough decisions about which direction to take a project certain times, but I'd say a lot of the time it's working alone.
So like what level of knowing what the thing you're looking at is that able to do? Like if I were to pick up some pond scum in some random third world country and scan it, would it know where it is, or would it know it was pond scum?
So that's a good question, and there's actually a couple levels to that, because for one, it has to be in your library, right? So one of the big things that people ask is, oh, could you use it for allergies? Could I scan this salad and see if there's peanuts in the sauce or something like that? Well, you'd have to scan a lot of salads and a lot of different sauces in order to train your instrument to pick up on that signature of the spectrum to be able to determine that. The other challenge is just the technology itself, how far, what the smallest, how trace amount of percent it could go to detect certain things. So NIR is typically kind of broader spectral characteristics, so it's a little less sensitive to certain things.
But maybe like one day this is like technology of the future.
Potentially, I mean, yeah, especially with our current setup, one of the things that we sacrifice for it to be so robust is more resolution. A lot of spectrometers are grading based, where now you have a grating and you have a bunch of sensors under it. But the problem with that is there's sometimes moving parts, like you might have a MEMS type of mirror that'll scan through wavelengths. It's a moving part. What happens if you go like that to it? Is it going to get out of calibration or things like that? But with us, it's all very solid. We have one filter that's attached pretty robustly to a detector. Yeah. So.
So you had a diagram that shows multiple layers, light hitting, the surface of the sample with multiple reflections and transmissions. So your data certainly, gives you this, all these peaks here, telling you absorption, transmission. Does your data also tell you how thick each layer possibly could be? Does it tell you the layer thickness and also any information on the interfacial roughness? Because I imagine, samples may not be so ideal. You're going to have a lot of, defects and boundaries and
Yeah.
interfacial roughness.
Yeah, so a couple of things to address your first or your second question actually about the how different samples have different textures. A lot of that came into the optical design of this. How do we make sure that there's uniform light that's illuminating all of the pixels under it? If you have something that's highly specular where you shine it, it's like a mirror, then you might have hot spots. So we use special optics in order to remove those hot spots and uniformly spread light throughout. In terms of detecting, I'm sorry, could you repeat the question regarding the layer?
Can you also extract or get the information in terms of, thickness of each layer? Imagine you have 3 layers. Can you get the thickness of each layer?
Is this no longer with the Michener or just in general, or?
And the point is you design it with a certain
Yeah,
thickness,
so the point is that you design your filters based on these layers in order to get a certain wavelength to transmit. So I guess you could theoretically reverse that and say, I have this wavelength peak that's being transmitted and must be this kind of thickness. But once you get into optical coatings, they could be pretty complex with many layers. So that could be a very difficult thing to reverse that. Yes?
Typically you have, am I thinking correctly, say that each of your different little colored squares was a different filter?
Yes, that's correct.
And how many layers typically does one of those colors have in the actual manufacturing? Is it hundreds of layers or 10 layers? Or?
Well, in terms of, for each of these, there might be, this just shows a very simplified version. In terms of magnitude of layers, I don't really know, to be honest. I would say it's on the order of, actually I don't know. I don't want to say and be wrong, and I don't want to mislead or any sensitive information. A lot of this stuff is kind of proprietary in terms of design.
So are you saying it's proprietary, or are you saying you don't know, or you don't want to tell us?
I don't know, and I don't know if it's proprietary, so I prefer to not say, or prefer to not guess.
The analysis was maybe linear analysis, in the sense that you could, if you had different samples, the final result is a linear combination of those, or is linearity not applied?
I mean, if you mix samples together.
Yes.
So if you mix samples together, what was your
Well, I mean, when you take the data, are you assuming that the samples are thin enough that you could assume linearity in terms of how you analyze the data, or you have to know the structure in the sample, vertical structure? Because you may just be seeing the surface of the sample, not the whole sample.
So you're saying if we're measuring with the, they're on here. If we were measuring one of these samples here,
Right.
yeah, so that's a good question. Uniformity of the sample, it's assumed that it's going to be uniform, but you could train, if for instance, there's some skin layer that's going to be different from the meat, you could train the Michener to, based on that spectra. With the cool thing about NIR light is it penetrates deeper than regular visible light. So a lot of times you could get
kind of linear, and then you get a little of everything. You don't just get the surface.
Yeah.
Are there other questions? Could I ask a quick question?
Yeah, sure.
So your colleagues, so you have a master's in physics. Does your company hire bachelors in physics or any students?
So
PhDs?
the different, there's a lot of different recs that are out there. Depending on what position you're going for, they hire people right out of high school to do tech work. Then there's, the engineering tech level, which sometimes comes with the bachelor level. I work in the R&D department, so a lot of people there have Actually, there's a lot of people there who just have a bachelor's level, but there's also a lot that have PhDs over there. So it's a good range of.
Do they hire any former Sonoma State students you know of?
Yeah, so there's a couple Sonoma State folks that work there. One is Cliff Alapa. He works in our MCL, our metrology lab, our material characteristics lab. And then there's Casey White, and I think he still participates here occasionally doing some kind of work at Sonoma State, and he's one of the program managers. That's all I could think of now, but I'm sure there's plenty more.
We have one sitting right here.
Yeah.
Oh yeah, yeah, that's right. I'm looking at you like, yeah, right? Is that it? And he's also a VIB employee.
All right. Are there any other questions?
So,
If not,
actually, one. So if you have to boil down your physics education to one skill that served you best in this job, what would you say it was?
One skill.
Other than optics.
Yeah, I think one cool thing about physics is you're really learning how to learn. You get introduced to so many new topics, you kind of start coming up with the method of, okay, you got to know, you have to figure out what you don't know in order to learn it, right? And so working through that process of what do I need to know to understand this, I think that was really helpful, especially because joining this lab, or joining this department, I really didn't know anything about spectroscopy or thin film coatings or things like that. And so yeah, just kind of knowing what direction to focus your energy. That's kind of a very vague thing, I know, but I feel like that I really got that out of physics. I think a lot of math, learning a lot of math is very useful. If anything, it helps you to think logically about things that aren't even mathematical. But also for a lot of applications, math really helps to understand it better.